Okay, can you hear me again? Are you back from the break?
Yep, can hear you.
Great. Okay, now let's proceed with the last 1.5 hours, or better to say just 1 hour and some more minutes, of the regular part of the mathematical preparation course. We're still dealing with the topic of vectors, and our next task is going to be task 52. Do you have any questions about this task? Actually, it's a pretty easy one, but nevertheless, we could go over it if you would like to. No one? Yeah, basically it shouldn't be too difficult. Of course, we are dealing with three-dimensional space in this class, and you have a cube with, of course, every edge of the cube has the same length. In this case, it's A. And in order to set up the position vectors of the vertices of this cube, the most of them shouldn't be too hard. So let's go with some of them. What about the point P1? What would be the position vector of point P1?
One meant which letter comes first for the Harvey in three-dimensional. So we at school learned that the depth came at first.
Okay.
So like P4 would be the first.
Actually, the origin of just a second, I have to snip that from the PDF.
Because I already looked at the solution and was confused because I learned it different.
Okay. Yeah, actually, this is another perspective on the coordinate system, on the entire coordinate system. So if you draw, come on. Doesn't work. I did copy it, right? Copy. Yeah. Yeah, actually, there is a definition on how to draw a three-dimensional coordinate system. So this is actually not the way you do it, for better that you can even display a cube in the normal way of drawing a three-dimensional coordinate system. You wouldn't be able to see the shape of a cube. So actually, I learned it the way at school and that the shape of a three-dimensional coordinate system. And this one is the x-axis to the right, just as before. Then the depth of this one, which goes back, is y, and the height is
I have to get a little bit closer again.
Oh, okay. Can you hear me now?
Yep.
Okay, great. So this one which goes to the right is x. The one going into the depth, so to the back of the page, is the y coordinate, and the height of the shapes are given with the z coordinate. Did you learn it the same way?
No, we
maybe you
did it like x, y, diagonal.
X1, X2, and X3. Yep. So that's how the Bavarian and the Baden-Württemberg students learn it. So did you do it like this?
Yep.
Okay. So yeah, you will have to get used to X, Y, and Z now. So I know that it's done with X1, X2, and X3 in some states of Germany, but yeah, X, Y, and Z is the method I learned, so it would confuse me to get used to X1, X2, and X3 right now. Yeah, but this is also done in some countries maybe. But now X1, X, X2, Y, and X. Okay, so in this case, you of course you now have to get used to this, and that's a good way to practice this. So what would be the coordinates of point P1, or better to say the local vector, not the local vector, the position vector.
That's 0.
Yeah. So this is 0, 0, 0, because as you can see, the coordinate system is exactly built up from this point as its origin. So this is the origin of the coordinate system. And that's why it has the coordinate 0, 0, 0. And regarding the fact that we're speaking of vectors, you can also, or people also thought of a certain symbol for representation of the so-called zero vector. And this is this as a symbol. So you can write this O with some, Schnörkel. It's the German word for it. To represent a vector which just contains of zeros as elements. Okay. What about point 2? What would be the position vector of point 2? P2.
Zero, 1, 0, 0.
Okay. Yeah, I think P4 and P5 should not be too hard for you to do. What about P3? Let's do this.
1, 0.
Correct. And what about, let's say, P7?
All of them are 1.
Yes, so 1, 1, 1, because you would have to go until, of course, it's not 1 all the time, but it's 8.
Yeah.
But I didn't think of this.
I just thought I missed 1 point, so that's why I always repeat 1 and 0. Yeah, 0 is correct, by the way.
Of course, it would also be correct to write 1, 1, 1, and then multiply A.
Yeah.
So this would also be a possible way to do it. But anyway, that's the way you should do it. I think it shouldn't have been too hard for you. So I would like to proceed with the next task right away. Let's me. Hey. So this was it 42? No, 52. 2. No, it was 42. Just a second. 52. I did it wrong up here. Then. Please. Let's start again. Okay. Then let's proceed with the next task, which is 53. I think 53 is now dealing with the topic of unit vectors. So do you have you dealt with the topic of unit vectors already? Oh, this is the solutions. Yeah. So the task 53 wants you to find the unit vectors corresponding to these given vectors. So what can anyone give me the special property of a unit vector? Why is it called unit vector? Who remembers the special property of a unit vector?
Okay. It's written in the chat.
In the chat, but I can't always see the chat, but I now opened it. So in the chat, there is a message saying that its magnitude, the magnitude of a unit vector, in German it's Einheitsvektor, the magnitude of this unit vectors is always 1. Yes. So how can we find out about the length of a vector, and if it is the length of 1? So which condition needs to be met in order to say the length of a vector is 1? Of course, we already learned how to determine the magnitude of a certain vector. So the magnitude of a vector can be written like this, as we already found out. And we calculated the magnitude of a vector by just taking its coordinates, square them, and add them together. And at the end, we'll take the root, the square root. Okay, so if for, of course, for a equal to x1, x2, xn. Okay, yeah. How does this help us in order to find the unit vector to the given vector a equal to, I think it was no. Okay, 214. No idea where this can be from, but 214 is also a good thing to do. Yeah, how to find the unit vector to this corresponding to this vector?
Square root of.
Okay, so at first you would determine the magnitude, right? So the,
Right.
the magnitude of A
Mm-hmm.
would be, in this case,
4 plus 1 plus 16.
Correct. So consequently, the whole expression would be equal to the square root of 21. Okay, and what do we do now, having this magnitude? So what is the unit vector of A? Remember, we wanted to find a vector which points in the same direction as the vector A, but now the magnitude of UA should be 1.
Yeah.
So what do we have to do in order to find this vector?
Multiplying with square root of 21.
So you would just use the vector A, so 214, and multiply it by square root of 21?
Yeah. No, dividing.
Yes, better option. Okay, so let's check if that works. So if we divide all of the elements, or at least, or you could say you multiply 1 divided by the square root of 1, right? Dividing it. And if you do so, this would look like the following. So the vector UA, the unit vector of A, would then be 2 divided by, come on, 2 divided by root of 21, 1 divided by root of 21, and 4 divided by the same root. Okay, so let's check on the magnitude of this. What's the magnitude of this vector? Suppose we would have the same thing as before. And what would be the outcome of this?
1.
Yes, but let's derive it properly. So if we do the calculation, this would of course be 4 divided by 24 plus 1 divided by 21 plus 16 divided by 21. And if you would add all these together, it would be 21 divided by 21. 1. So you see, all you have to do in order to find the unit vector corresponding to an arbitrary other vector is to determine its magnitude and then divide every element, that is to say, the whole original vector by this magnitude. So, common thing to say is that in order to find the unit vector of certain arbitrary vector x would be to take vector x and divide it by its magnitude. A thing you can remember for later. Any question about this?
I have another question out of topic.
Yes, please.
You said Einheit. So does Einheit also mean unity in English?
Yes.
Danke. Thanks.
Yeah. So Einheit, it's Einheit in German, which is the same for our national holiday, which is Tag der Deutschen Einheit. So where GDR and BEPRD, that's on the name for West Germany, came together again in 1989, called Day of Unity, or Tag der Einheit in German. Yes. So unit and unity, the same word.
Thank you.
Okay. Any other question related to the topic of unit vectors or unit in general, unity? No? Not for the next topic, which is 5, calculating angles. Maybe very closely connect. No, it actually is not. Okay, it's not connected with task 55, but let's deal with or calculating angles. Basically, we already had that earlier today. So we set up a certain equation. I already told you that this would be a good way to determine the angle in which vectors intersect. So maybe it would be too difficult for all of you to apply just this formula. Of course, be careful that you don't not only this fraction function to whatever comes out here in order to find the angle. Yeah, but I don't know. Would you like to see one example for this application of the formula, or are you good just with the knowledge that you have to do it?
If nobody says anything, we could pass this example.
Yes.
Yeah.
I would say that.
Because we did it before, so I mean.
Okay. Yeah, we didn't do an example for it, but yeah, it's just applying the formula, and I think you should all be able to do this.
Yeah.
Okay. Next thing would be to check whether two vectors are orthogonal. So how can you check whether two vectors are orthogonal? I think we also mentioned that earlier today.
Yeah. So the scalar product is 0, correct?
Yes, scalar product, correct. So we need to make sure that, I think it's directly above. So we have to make sure that the scalar product of the two vectors is equal to 0. So this is completely sufficient to say that the two vectors are intersecting at a right angle. Okay, yeah, do you want to check upon this for one of the examples? So yeah, let's do example
A, please.
A. Okay, not B.
Okay.
Okay, so let's do A without writing anything down, actually. So what is the scalar product of these two vectors?
4, 8, 16, 20.
Yeah.
So yeah.
So 4, 16, and 20. So 4.
Sorry, negative
20, right? So 4 plus 16 minus 20 is
0.
0. So these should be orthogonal, right? Okay. Yeah. And what about the other examples? So what about task B? Okay. In this case, you would have to just a second.
Are these imaginary numbers, Simon?
No, they're not.
Just sign, right? That's why I had a fear.
So just variable names, right?
Okay.
All vectors, but they were not given in here. I, J, and K. Actually, I don't understand the sense of this task. Okay. Check with the solution. Okay. So actually, they also checked with the scalar product in here. 3 times 4 plus negative 2. The tasks again.
The important thing is here magnitude, right, Simon? Because
magnitude?
Yeah, I mean the I, J, K, it could be the direction, but the important thing is magnitude when we multiply two vectors. I mean,
when we're just
example
doing the scalar product?
Yeah, scalar product, sorry.
You mean the scalar product?
Yeah. I mean, that's why
you can't do the scalar product by just having these variable names.
Thanks.
So actually, that's not the proper thing to do. But I think what they wanted you to do is, okay, I think I, J, and K are the so-called, I don't know the name in English, but it's Erzeugenden-System. In German, it's Erzeugenden-System. I don't think I'll find that in the online dictionary. Yeah, it's a generating system. So you could call them a generating system, or the basic generating system of a vector space. So the generating system of a vector space. Well, you say the basic generating system of a vector space. So for instance, the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. They will make up a so-called generating system of a vector space, since a linear combination of these three vectors. So do you all know the linear combination?
Zero. I mean, sorry. If I say.
Sorry?
I'm just waiting.
Okay. A linear combination of vectors means that you apply real coefficient to the vector. So the elements of the vectors, and then you can add them together. So this is what's a linear combination is called. So this is basically the linear combination of vectors. So a generating system of a vector space is basically every set of vectors which could be inserted as the vectors ABC into such kind of a linear combination in order to receive any arbitrary vector part of this vector space. So vector space actually just means 2-dimensional, 3-dimensional space, and so on. So in order to make up a generating system of this vector space, you would be required to find as many vectors as the dimension says. So 2 or 3, in this case, it would be 3. And if you insert them into this term, so A times 1, 0, 0, plus B times 0, 1, 0, plus C times 0, 0, 1. With this, by inserting real numbers for A, B, and C, you would now be able to form any vector you would like to receive in 3-dimensional space. So this could be anything, since it would be A, B, C. So you would have a vector with real number, real number, real number, and that's basically every vector you think of in 3-dimensional space. Of course, there are a lot of different other possibilities how to make up a generating system. So of course, it would also be possible to use 200 instead of 100 vector, because you would still be able to pick up any arbitrary vector you could think of. But that's why I wrote down basic generating system. This system or generating system with 100, 010, and 001 is the most easiest way to find such a generating system. Okay, back to topic. Actually, we were talking about the vectors, yes, vectors I, J, and K, which are given in this task. So basically these, but I think they gave nowhere that I, J, and K are actually meant to be these vectors of the generating system, of the basic generating system of the three-dimensional vector space. So actually they wanted you to know that this is the vector I, this is the vector J, and this is the vector K in the task. Of course, they didn't give you that, but yeah, if I give it to you now, you should also be able to solve the task. So if you now know that I, J, and K are the vectors which make up the basic generating system of the three-dimensional vector space, then you should be able to prove whether they are orthogonal. Because if you have 3 times 100 minus 2 times the vector 010 plus 10 times the vector 001, shouldn't be too difficult to determine the resulting vector. So what would be the resulting vector A in this case? So if I have 3i minus 2j plus 10k, so with 3j, minus 2j plus 10kb.
Then 3, negative 2, and 10.
Correct. So this would be the first vector, and the other vector is filled up the same pattern. And the other one would then be 4i plus j minus k. And this would consequently be which vector?
4, 1, negative 1. Or 4, negative 1, 1.
Negative 1. Right. And what would be the scalar product of these?
12 minus 2 minus 10.
This would be 0. So I think that's what they wanted you to figure out, that I, J, and K are the basic vectors of the basic generating system. But yeah, of course, they didn't give it to you, and that's why this task was actually unsolvable. So I'm sorry for that, but I will text the person who's in charge for the task sheets that they added in there. So yes, this shouldn't be too difficult if you know that I, J, and K are these basic vectors determining the orthogonality of two vectors.
No. What's the reverse of orthogonal? Is there any term for it? I mean,
non-orthogonal.
Okay, just one.
No idea. So
Okay.
just for describing the fact that they are not orthogonal, I don't think that there is a proper term for this.
All right.
Yeah. No idea. There is a wonderful term in German for two lines in three-dimensional space when they not intersect. So two lines do not intersect in the three-dimensional space. The term is called that Vinci. Free expression. It's also used for houses which are blown by the wind, so they're then not standing upright anymore, but anyhow deformed. Then you can also call houses Vinci, and that's the way we use straight lines which do not intersect in any place.
Okay.
And
Thanks.
they are not parallel, but yeah, that's another story. But of course, it's also connected to vectors. That's why we can. Anyway, maybe we could go on with the next tasks. I think, yeah, it's just 56, 57, and 58 left here. Maybe 56 is another thing we could just discuss by talking about it. Yeah, what are the components of the unit vector E pointing in the opposite direction from A? Think about it for
Is it
a minute.
-1, 4, -3? Not.
Actually, this would be a vector pointing in the opposite direction from A. That's correct. So if you just multiply -1 to vector A, so if you take the vector -A, basically, this would give you a vector with the coordinates -1, 4, and -3. And this vector would point in the opposite direction of vector A. That's correct. And then they wanted you to find not only the vector pointing in the opposite direction, but the unit vector. And I'm sure you also remember how to find the unit vector. How do you do that?
1 square, -4 square, plus 3 square, root square of blah, blah, blah. And then
Yes, correct.
it's equals to 26 square root. Then dividing by 26 square root.
Correct.
Square root of 26, then it will give us the unit vector of E.
So this was the original vector, and the vector E would then be, you can do it by hand, -1 divided by square root 26, +4 divided by square root 26, and -3. Right?
Yeah, definitely.
Correct. So this one was not too hard. No, 50.
Yes, 23 or 4, 6. I don't
remember anything.
Yeah.
Okay.
Today
56.
I'm using my tablet, so I don't have also the
Yeah, I used to
PDF
have
sheets.
I used to have 3 screens during the last 2 weeks, and today I'm just having one. So it's more difficult for me as well. But yeah, let's proceed then. There's no question, because I would really like to make it to the word problems at the end. What about task 57, magnitude and direction? So determine the magnitude and the unit, okay, magnitude and unit vector of the following vectors. I think if there is no request, we have done this a lot now. Not pretty
Yeah.
sure if you really need this anymore.
No, I mean, we have done a lot of exercise,
Yes.
unit vector and magnitude. So
anyone who would like me to go through one of these? I'm also looking at the reactions. No? Okay. Yeah, then let's proceed with the word problems, because I especially like the word problem 58b, which is a very hard thing to deal with. Yeah, that's why I would especially like to go through 58b. But at first, is there any subtask of 58 you would especially like me to show besides 58b? A or C? Should we start with one of them? No? Okay, then let's start with 58b. So this is a very interesting one because, okay, also given the hint vector projection. Yeah, determine the component of one force in the direction of another force. So this is a thing which gets especially interesting. You all, I think, at least I think so, you all have to deal with physical tasks as well in the studies. So 58 B gives you the following values, or maybe I'll copy it again. Okay. be the whole thing. Wow, that was big. No. Okay, then let's keep it like this. Yeah, task 58b. Determine the component of this force in direction of another force. So what would be the first thing you would do about this task? What would every physics teacher do at first?
Draw it.
What?
Draw it, right? So we would need some kind of sketch, right? So let's do that kind of sketch. Maybe you've already dealt with this in physics. So every force, we already had another topic, another task related to forces, but every force actually is a vector in physics. So whenever there is a force, you will always be dealing with vectors. In physics, they used to simplify it for 7th and 8th grade students because they didn't used to deal with vectors back then, but actually every force in physics is a vector, a three-dimensional vector. Okay, so we have two different vectors now. Of course, they have 3 dimensions, both of them, but since my screen is just a two-dimensional plane, I will keep it with 2 dimensions. But the good thing about vectors in general is that most of the equations and rules and formula which can be set up just by deriving them in 2 dimensions, they also apply in higher dimensions. So if we now find some kind of formula for this projection, we might also be able to use it. So we will be, but let's check on this. So let's say these are the 2 forces that we are dealing with. Let's say this is force 2. And this is force 1. So how could we now find the force that we are actually searching for? What are we searching for, actually?
A component.
So we are looking for some kind of component. Actually, I've done something not too good about this sketch. Just a second. But F2 looks like it was the x-axis of a coordinate system. I don't know if I can tilt it. No, I can't. Really? Let's do this. Yeah, so we would have to find a force in the direction. That's what the task says. In the direction of force F2. So we already know that whatever we are searching for is a force component of F2. So the vector that we want to find, because we are looking for a force, and the force is always a vector. The vector that we are looking for has the same direction as F2. And if we want to find that vector, which is a component of vector F2, what do we have to do in order to find this component of force F2?
Just adding and subtracting. I mean,
yes, that would be a good thing to have. But
connecting the vectors together.
Actually, you would have to first build this vertical line from the tip of F1 to the force F2. So that's what the task actually wants you to do, to find out the component of force F1 which points in the same direction. So this is the arrow representing F1, and you want to find the component of F1, which is pointing in the same direction. Physics every force can be split up to different forces. We did that earlier with topic 52. And we learned that if you have multiple elementary forces, you can add them together and receive one composite force. And in this case, we're doing the exact opposite thing. So actually, we could split up force F1 into its components. So you could think of it like doing this. Okay, let's do it again. Split it up like this. And these two green arrows, these two green vectors, would then, if you add them together, would make up your original force F1. See that? Okay, but now we're actually only interested in the component which points into the same direction of F2. So we are not interested in this force. We will erase it again, but you can think of this as the splitting up of the force 1 into its components. No? Second.
Okay, I see.
Yeah, could you now think of any approach, a mathematical approach on how to find the components of this green down there?
Firstly, we need to find the angle in order to find the adjacent of F1.
So we could have a look for this angle. I would call it phi down here. Yeah, that's a good thing to do. But maybe there's another thing we should set up first. So we need some kind of basic equation that we should work with.
Simon, your voice is a little bit shaky. I mean,
okay, I'm sorry. Yeah, my microphone is best of a kind. What could be an elementary equation which we could work with in order to find this green arrow? So let's just call this. The elementary equation for fx.
Not sure, but x times f2.
Actually, we don't even need to do that. Just, I'm sorry.
Okay, so it's a wrong approach. Okay, I got it.
You were talking about this angle. Maybe that's a better thing to do. So let's find some kind of expression for this angle.
Okay, then it will be cosinus phi.
Sine of phi?
Times sine of phi. No, cosinus.
Yeah, I also think cosine would be better.
Times f1. Or, I mean, okay, is it cosine?
So we have, of course, a right triangle here. So we have a right angle. So cosine of phi would be, go again.
I don't know the angle. Because are we approaching fx, right?
Yes, we want to have a certain equation containing fx. That would be good.
Okay. I got your point. Sorry. Yeah. You're true then. So, cosinus phi will be adjacent. I mean, over. I forgot the term. Hypotenuse.
Adjacent, yes, adjacent divided by hypotenuse. So what would be the adjacent in this case?
F1 times
F1.
Oh, yeah, F1 times actually magnitude of F1. Didn't know. I'm confused. Sorry.
Isn't it fx times f1?
By times F1. So the adjacent,
over. Sorry.
Yeah, we're just talking of this triangle. And in this case, the adjacent of this triangle is just the magnitude of fx. You see that? So the length of this green arrow is the adjacent of the right triangle. And what about the hypotenuse? The hypotenuse of this triangle?
F1.
Yeah. And basically the edge of a triangle only it doesn't have vector values or vector properties. It just is a number, the length of the edge. So that's why we also have to look for the magnitude of F1, because we only are interested in the length of the arrow and not in the vector properties. Okay, so that's something we could maybe work with. So if we transform this, maybe I'll do it right now because there are some steps to go, but maybe you can follow what I'm doing. Just a second. So at first we can transform this by multiplying with the denominator. So multiplying by the magnitude of F1 would give you magnitude of F1 times cosine of phi being equal to the magnitude of Fx. Correct? Correct.
Yeah, it's correct.
Okay, so the next step that we could now do is that we somehow extend this equation. You may remember this from when we simplified terms and fraction terms, but in this case we will also do it. So we'll just multiply something to both sides of the equation. It's just something someone invented a long time ago, and then people said, oh yes, that's true, let's do it like this. So in this case, we would have to multiply second, keep in mind. I'm sorry, I just saw that this might be better. Second, I have to look. Yeah. I was confused, sorry. So we would have to bring F2 into the game here. So if we just do this, this would also be correct. Nothing wrong about this.
Mm-hmm.
Next step would then be to see or to spot the reason why I did this a second ago. So what about this expression? Do you remember this? Maybe from above. Look at that.
Yes.
The magnitude of vector A times the magnitude of vector B times the cosine of the angle between these two vectors. And that's exactly the same thing that we are facing right now. So you have the magnitude of F2 times the magnitude of F1 times the cosine of phi, which is exactly the angle between F1 and F2. As it is the angle between Fx and F1, between Fx and F1, but it's also the angle between F1 and F2. So we can now say that this is equal to the scalar product of F1 and F2. Still nothing wrong about our equation, right?
Yes.
Okay. So how could we now go on with this derivation? We could transform it again. So if we transform this by dividing by f2, we would only be left with the magnitude of fx on the right side of the equation. And fx is the vector that we want to find. Remember that. So this would be the scalar product of f1 and f2, now divided by the magnitude of f2. And on the right side, it would still be magnitude of fx. And then we would have to do another piece of magic. So the first piece of magic was this f2 being applied to both sides of the equation. And now we would have to do the same thing again. Actually, you could have a look at the two vectors fx and f2 again. So if you consider these two vectors, there is one property of them, which they're both pointing in the same direction, right? And you learned something about unit vectors earlier today. So a unit vector was a vector pointing in the same direction as another one, but it always had the length of 1. So the magnitude of the unit vector is 1. So you could set up the following equation: vector fx divided by its magnitude is the same as the vector f2 divided by its magnitude, right? Because this would both be equal to 1. Oh, not 1. Of course, not 1, but the resulting vector would have the length of 1. So this was not true, what I wrote down, but the vector which would be the result of this would have the length or the magnitude of 1. So how could we now transform this equation? We could transform this to the following. Of course, we want to replace the magnitude of fx because we are actually not in the magnitude of fx, but in the actual vector. So in order to transform this, we would have to bring fx to the other side and f2 and magnitude of f2 to the other side. And this would lead us to the following expression. Who wants to conclude?
Magnitude of f2 over wait a second. No, I mean fx divided by I'm just checking fx f and not the magnitude of f2, but it's fx. Yeah, yes, sure. Over f2.
Sure.
Vector of 2.
Correct. So this would be this equation transformed. And if we now substitute the magnitude of f of x in our equation here with this term, then we would being equal to magnitude of f2 times vector fx divided by f2. And now we can divide, or better to say, we multiply by f2 divided by magnitude of f2. And then we would only have f of x left on one side of the equation. And this would then be equal to the scalar product of f1 and f2 being divided by f2 times magnitude of f2 times magnitude of f2. So in fact, we would have magnitude of f2 squared. And this whole expression times f2. And now writing this down a little different, or a little, yeah, you have to pay attention on one special property of this expression. So please always be aware that this dot represents a dot product, so a scalar product of these two vectors, while this is still a normal multiplication. So you have both of them in here, and please do not have the idea to pull these together to something like a squared vector, because that's nothing which exists. There's nothing like a squared vector. But if you do the scalar product at first, then this would be a real number, and you will divide it by a real number, and then you would have this real number as a factor of the vector f2. And that's exactly how things work in our task, because we already figured out that fx is just a component or a part of f2. So it's pointing in the exact same direction as f2, but it's only scaled down by a certain factor. So this is actually a good thing, or a good point where we end up, since this is just a real number multiplied by the vector f2, which means that we are scaling the vector f2 by a certain number. And that's exactly what f of x does. Okay, so let's check this for our example task. Then be equal to what? Just a second, where's the task here? So we have the two vectors, f1 being 200, negative 300, and negative 100, and f2 being negative 10, 30, and 120. So these are our two vectors. And now we can insert them into our term, our equation. To do that, it looks like the following. Which down here is supposed to find the magnitude of f2. And this will be used as a factor for force 2. This gives me the scalar product of these two vectors, the numerator of the fraction. Of course, without the help of a calculator. You remember how to calculate the scalar product out of two vectors given their components? You may remember that you would have to multiply the first component plus, then because there's negative and positive, we have to use minus in here, and there's another minus 120 added to zeros, and this would be negative 33,000 up there. Yeah. And for this. So the square product would end up to be negative 33,000. What about the magnitude in the denominator? What is the magnitude of F2?
It's like the root of 15,400.
Or
15,400.
okay, yeah, if you say so. So it would be 100 plus 900 plus, yeah, I don't know what 100 squared is. So what did you say? Again? So what was your magnitude value? Okay, so now I have to write it down again like this. So this would be 110 squared plus 30 squared.
Ah, sorry, I was muted. 120, 124.1.
Okay. Wait. 124.1 is just the magnitude, right?
Yes.
Yes. So as you can see, we have to square this. And in order to determine the magnitude, we did something like the square root of 10 squared plus 30 squared plus 120 squared. And now we have to square this whole thing. And when we are doing this, you can recognize that it's just canceling with the square root we used in order to determine the magnitude. So we can just leave it with this expression. What would this expression be equal to? So there wouldn't be a comma in there. Calculate this again.
15,400.
15,400. Okay. Actually, we were up here. So this was still the same for 120. Now, yeah, we have to calculate the fraction. Can you do this for me as well? So minus or negative 33,000 divided by 15,400. What is that factor? Somewhere around 2 point something. I don't hear anyone. Maybe you're, but let me do it.
2.14.
Okay. So 2.14 times our vector, and you should use a calculator for it as well. So to do this. Second one then would be I don't have a calculator. Could be somewhere around 60.2.
For this 64.2.
The third component.
You're getting silence again. 256.8.
Correct. So I don't know the correct answer. I hope you insert this into the calculator. So this would then be the vector being the component of F1 pointing in the same direction as F2. And I would like to give you a very short hint on where this applies in physics. For example, if there's something like a hill or a mountain, and you have now it's about drawing again. I can't do it. You have something like a car or a bike riding on this tilted surface of the hill. At least I could draw it if one would let me. So if I have the bicycle here, or let's say a car, it's a car right now. Let's just treat this as anything. I don't know what it is, but you have this vehicle on your hillside, and of course this vehicle has a certain weight, certain gravity. The gravity pulls it downwards, so this would be the weight of the vehicle. So yeah, I only know the German term Gewichtskraft. This pulls down, and in order to determine the force which pulls the vehicle down the hill, of course this force pulls to this direction, you would have to split up the weight, so the Fg, in two different forces. So you have to determine the component of the force Fg which points in the direction down the hill. So in this direction of the green arrow. And that's a very common thing where you apply this splitting of forces. I hope you can imagine that. So you actually would have to do the projection of Fg onto this actually not this arrow, but on this line. So you would have to do this with this right angle, and then you would have to determine this arrow. So that's a situation where this, what we just did with the task, applies. I know that this is a very extensive and exhausting derivation of this formula, but in the corresponding video in the material folder, they just gave this equation, but I wanted to show you where it comes from, and this is the derivation of this formula. Do you want me to re-explain one of the steps, or are you good with what you've heard? I can open the Zoom meeting again. So if you could give me a quick reaction, if that's sufficient for you. Okay, green reactions. All right, yeah, basically our time is over for today. So if there's no other question, I would like to leave it with this and not go through one of the other subtasks of 58. So because subtask C again deals with forces and the combination of four elementary forces, and we already did this when we talked about task 52, and 58A might have been another interesting task, but yeah, K deals with a triangle, and one interesting thing you might want to know, or you might need to know, is that there is a certain formula for determining the area, surface area of a triangle. So if these vectors make up a triangle, so it only needs two vectors to specify a certain triangle. So the third edge would be given just by connecting the two edges or the two tips of the vectors. And the area of such a triangle made up by the two vectors A and B, this area could be determined by multiplying 1/2 times A times B. Oh, so this is a dot product again. Times, oh no, just a second. I think it's just 1/2 times A times the sine of the angle between these two. But I have to look it up again. But there's a formula like this. No, it doesn't work again. Yeah, but it should be, I think it should be right. So 1/2 times A times B, so A dot B dot product times the sine of the angle between these two. Second, let me check it. Yeah, okay, this is another way to determine it. So that's the cross product, but we didn't talk about the cross product. No, actually, I was searching for this other term. Where is it? I can't find it by now. But it should be something like this 1/2 times a times b times sine. Maybe there. The sine of alpha. So yeah. Okay, actually you would have to apply the cross product in there. But so this is not actually true. So you would have to find out the magnitudes. So like this, it's true. The other thing you could state for the area of the triangle would be a cross product B, but we didn't deal with the cross product so far. So this would be another way to describe the area of a triangle, just for later, if you want to remember this already. But this would be a thing that you could calculate right now. Okay, yes. So any question left? In the chat, there's a message. Can we still have access to the Pro-Tree? Yeah, that would have been a thing which I would bring up tomorrow again. You will have access to all the folders and to the VMin page. It should at least be accessible for you until next semester when the next preparation course starts. Usually the people who are in charge for the VMin page are then rearranging all the rooms, and most of the cases it will not work after then. But for half a year it should be it should remain like it is right now, so you still have access to the page and to all the materials. Yes, and someone also wrote that I wanted to make another announcement for tomorrow. Yes, I wanted to do that. I actually did it on Friday, but I will repeat it right now, and I will post something into the announcement channel and that later. Tomorrow will be our last day of the preparation course. And on the last day, you will at first have the possibility to go through the assessment test for one more time. And I will give you the first 105 minutes of our tomorrow's lesson time for this. So I will not join the meeting. Sorry, I will not join the meeting at 4:30 as usual, but I will join on at 6:15. So you will have exactly 105 minutes for doing the test. Yes, it is the same test as in the first meeting, and you can still access it via the link on the VMin page. And yes, it's completely doesn't matter to me when you are taking the test. You can also take it right now, or you can take it tomorrow in the morning or during the day. But I will still give you the time from 4:30 till 6:15 tomorrow to go through the test again, and then we'll check upon your results and if you have made improvements. And afterwards, I will give you a short introduction on the topic of complex numbers. And afterwards, it will be the end of this semester's preparation course. But yeah, as I said, I will post that into the announcement channel once again later tonight. Any other question? And unfortunately, I will not be accessible during the time when you're taking the test tomorrow. So I will not be accessible before 6:15 since I'm on vacation, and I will not be front of my devices all the time. So I hope everything is fine regarding the technical aspects of taking the assessment test. So yeah, there's no further question. We'll meet at 6:15 tomorrow. And yeah, I wish you a nice evening and have fun taking the test one more time.